So let's see. Solving the separable ODE gives us, well, let's just rewrite it how it appears. So it become, just rearranging a little, 1 over 6 square root of Prandtl minus 1 over 30 times Prandtl times delta t d delta t equals 2. K over rho c is alpha over u infinity dx. Then we can take the integral of the left-hand side and the integral of the right-hand side. So the integral of the left is from 0 to delta t. Integral of the right is from 0 to x. And then that integral would give us, let's see, this stuff again. 1 over 6 square root of Prandtl minus 1 over 30 Prandtl times delta t squared over 2 equals 2 alpha over u infinity times x. Okay. Then we can solve for delta t, which was our ultimate goal here. So delta t is equal to the square root of 4 alpha x over u infinity times this, we'll call this parameter a, where a is equal to 1 over 6 square root of Prandtl minus 1 over 30 Prandtl. I don't want to write a bunch of times. So yeah, so now you give me a position x. Prandtl is a property of the fluid that we can assume. You can compute the delta t. And then we can get the heat transfer coefficient. So then carrying this out to the useful result, we would say, I want to know h. So h is going to be related to that expression of Fourier's law, which is up here on the top. H would then have to be 2k over delta t, right, based on our assumed temperature profile. So h equals 2k over delta t. Substitute in the expression for delta t, and we get h equals 2k times square root of u infinity times a over 4 alpha x. Then the Nusselt number would also be useful, I guess. So Nusselt number, Nusselt, is equal to x h over k, which is going to be x over k times 2k square root u infinity a over 4 alpha x. So then simplify that down, and that gives us a square root of u infinity a x over alpha. So, okay, so this is good. I guess we have now an expression for a Nusselt number. Normally, the Nusselt number for the thermal equation is going to be in terms of a Prandtl number as well. So we can get there. We can introduce a Prandtl number. We have thermal diffusivity. We have parts of a Reynolds number. So let's multiply the inside of this by the viscosity, right? Viscosity over itself. So that'll help us kind of normalize this a little bit. Okay, so if we do that, we get, let's see, multiply, bring this over, and multiply this by nu over nu. And then that's going to give us square root of Reynolds times A times Prandtl number. Right? Or another way of saying that is, again, square root of Reynolds times Prandtl number times 1 over 6 square root of Prandtl minus 1 over 30 times Prandtl. Okay? That's our correlation, right? This is, if you were to go need a correlation for Nusselt number, this is what you would then use. Or correlation is kind of the wrong word, but this is the relationship. So we can compare this to the known exact solution and see how well we did. But there's one thing that I want to talk about before we move on. It's something you'll need for your homework. So we've gone through this, and we actually came up with an ODE that was separable that we could solve. what happens, as it will in the homework, when you get to a point where you can't solve the ODE explicitly, or you can't separate the ODE? We'd have to use a numerical technique. Okay, yeah?
Would that, when we put a back in, it would be like square root?
Did I? Yep, thank you. I'm sorry. Good catch. Square root of that. So if we have an ODE that we cannot solve separately, you can solve it numerically. Remember what we did for our numerical techniques in like 0D transient, where you'd say, I can put in to Python a solve, the function was called solve IVP, which I think we used. So solve underscore IVP. And the arguments for the solve IVP were a function name. So function for d, so in the transient problem, it would be, give me a function for d temperature, d time. And then once you evaluate that, you pass that. Here we're looking for d delta t dx. So a function where you can evaluate d delta t dx. So I guess, looking up at our ODE, I guess looking back at our ODE on the previous slide, let me just flip back here. This ODE here is what we said we could separate. If you can't separate this, you'd have to solve for d delta t dx on one side of the equation. What would be left would be the contents of your function, right, that you would use to evaluate. So you get one side d delta t dx, the other side everything else. Then you come back and plug that into this solve IVP. So you need that function. You need to have a range. So let's say from a range from the leading edge, 0 or close to 0 will be the case, to the position you want to evaluate, so x or L or whatever it is. And then the last thing would be you need to give it some initial delta t. Normally that would be 0, but for the ODE that you guys are going to hopefully derive, it will have delta t in the denominator. So if you pass 0 as your initial delta t, it will complain. What you need to do then is solve IVP, give it the function, start at a position that's not 0 but close to 0, and start with an initial thickness that's not 0 but very, very close to 0. Okay. So once you do that, what it's going to do is the function will step through and sort of build the boundary layer, right? It's integrating the value of d delta t dx, and then it gives you back the boundary layer thickness as a function of position. So that's how you're going to get your boundary layer thickness. You do the same, same approach you did for the transient problems, but it's just applied to this domain instead. Yeah, Doran.